Okay, we are continuing on here with equilibrium. Last time we did some examples that involved either calculating Kc or Kp. And as we've talked about, they're both basically equilibrium constants, and all equilibrium constants are really the same thing. They're basically our concentration of our products over our reactants. Obviously, we do take the coefficients as the exponents, as we talked about. Now, as we saw, we can obviously do one with concentrations, which is sometimes referred to as Kc. In certain cases, we can use pressures when we're dealing with gases, and we could write an equivalent sort of expression which deals with the partial pressures of everybody present, and that was known as the Kp value. Again, we would still take the coefficients as the exponents when we do it. I think I might have mentioned it earlier, but as we get into these next parts of these calculations, typically speaking, atmospheres is usually the units you kind of want to use when you're doing any type of equilibrium calculation for pressure and stuff like that. Especially as we get into solving for equilibrium pressures and stuff like that. Definitely you want to make sure everything's in atmospheres. That's usually the best approach there. Again, even if it sort of says some other unit and asks for some other unit, when you do sort of the equilibrium part of the calculation, atmospheres is usually what they need to be in when you're doing that part of the calculation. There's a relationship that we use a couple times there in some of those examples to go between these two. And again, it looks something like this. And that's our Kp value. That's our Kc value. Once again, that is the gas constant. That is this guy, basically. That is our temperature in Kelvin. And once again, as we talked about a number of times, we do want to make sure that we do take the moles of our product minus the moles of our reactant. Remember, obviously, it is just gases we're dealing with that. So it's got to have a G next to it to become a gas or be a gas. And it is important to do the products minus reactants because the actual sign that you get is really important, mathematically speaking. Again, if you get a negative, that is a much different math sort of operation than if you had a positive number there for delta n. So you do not want to just sort of take the difference and ignore the sign because, again, you will probably get it wrong. We also talked about the idea of large K values, right? And again, if you have a large K value, that means when we reach equilibrium, it is mainly products that will probably be present. And if we had a small value, it would be the opposite, which obviously would be reactants present. Any questions on any of that stuff we did last time? I think we did a few examples there after we took the quiz, I think. All right, we are then continuing on here. And that is not where we want to continue on. There. I clearly went the wrong way. Let's do this. There we go. Yeah, that's where we left off. There we go. All right. So what we want to talk about next is actually an important sort of application of equilibrium constants and the idea of sort of manipulating equations and how that affects the equilibrium constant value. So, for example, as we know, and as you probably know from like Hess's law and all those good things, not all reactions do take place in sort of a one-step process. Sometimes it takes several individual reactions, kind of like what we talked about with our reaction mechanisms there, to get us to an overall reaction. So there are going to be situations where you will be given perhaps an overall reaction, and you may be given some individual reactions that occur and their K values. So you might need to manipulate those reactions to figure out what is the K value of the actual equation you're looking for. So if we have these two equations and we add them together, when we do add them together, anything on opposite sides of the arrow will cancel. And that will give us our overall reaction, which is A plus B goes to E plus F in this case. And the equilibrium constant there for the overall reaction would be written as E times F divided by A times B. Now, how do we get to this sort of expression from our individual equilibrium constants for each of these steps, it is actually multiplying here. So it is different than like delta H where you just add them. In this case, when you add two reversible reactions together to yield you a third reaction, to get the equilibrium constant for the third guy, you actually would multiply them. So if we took both of these individual expressions for the first equation and the second equation, if we multiply them, those two will cancel, and that will leave us with the actual equilibrium constant expression that we have. So if you sum up two or even more reactions together to build an overall reaction, and you want the K value for that new equation, you basically just multiply all the K values together. So that's a really common thing that sometimes you have to do a lot. And it's also a very common thing that people screw up on because they have in their head like delta H where I just add it together. So here we do need to multiply and not add in that particular case. Any questions on that there? Another very common thing that sometimes happens when we have a reversible, our reversible reaction is, maybe we really don't want the reaction the way it's written in the forward direction. Maybe what we're really looking for is the reaction in the reverse direction. And if you do that, how it affects the equilibrium constant expression is it actually becomes 1 over the K value of the original one. So if we were to write our expression here for the top equation, that is our expression, which would be our products over our reactants. And it does give us this value. It doesn't really matter the number for this, but we get this number here. Now, if we wanted the NO2 to be our reactants and the N2O4 to be our products, basically we would write this expression. And the relationship between those two expressions is basically 1 over the original sort of expression, if you will. It's inversed. And we take 1 over K gives us a 216. It is important to note that when you see values for the equilibrium constant, like for example, when you see this value for the equilibrium constant here, it is specifically for exactly how that thing is written. So it's specifically for how that guy is written, with the N2O4 being our reactants, the NO2 being our products. If you were to state the equilibrium expression for the guy on the right, it is actually this number here would be the correct way to do that. And that is specific for the way this reaction is set up, where our NO2 is our reactants and our N2O4 are our products. So when you do see an equilibrium constant value given to you, it is again specific for exactly how it's written, and also a temperature as well. It's specific for when you see it. So if you're talking about sort of the reverse reaction there, you would need to use the 216. And if you're talking about obviously the one on the left there, you would use the 4.63 times 10 to the minus 3. This is also very different than what you do with delta H, right? When we reverse a reaction with delta H, we change the sign. And that's, again, a common error that people make when they do equilibrium. So here, if we reverse a reaction, you got to take 1 over the K value to get the new value for that reaction. Any questions on that there? Now, obviously, those are two things that we could do. We could add together two equations. We could also reverse a reaction. A couple other things very similar to what you could do, like when you're doing Hess's law, is sometimes you may need to multiply an equation by a common number, or you may need to divide an equation by a common number. And that also affects the equilibrium constant value. So for example, if we had our generic A plus B goes to C plus D, and I write my equilibrium expression here, which would be C times D divided by A times B. But I decide that I don't really need, say, 1A, but I need maybe 2 A's. So I would multiply that entire equation by 2. Once again, here, this will differ from enthalpy, because normally in enthalpy, you would actually just multiply the K value by 2. But let's see how it actually is affected here. If we were to write our new expression, it would be C squared times D squared divided by A squared and B squared. So by multiplying the top equation by 2 gives us this equilibrium expression. What is the difference between the original equilibrium expression and this one? It is the square of it. Yes, so we squared it basically. And that is because we multiply by 2. If I multiply by 3, it would then be cubed. Yeah. If I multiply by 4, you take it to the fourth. So in equilibrium expressions, how the constant changes is if you need to multiply by a common number, then you take the equilibrium constant to that common number. So if you're doing a little multiplication, you take the equilibrium constant to that common number, and that is how it adjusts. Clearly, division would work the same way. If I decided I started with the second equation, but I just needed one of everybody, that would then take me back to the original equation, right? And the difference between the k value on the second equation and the k value on the first equation here is, it is the square root of it. Yes, so that is the square root of it. If I had to divide by 3, I would take the cube root. Yes, 4, fourth root, and so forth. So if you are dividing, you basically take the k value to whatever you divided by, basically the root of it to that number. And if you multiplying, you again take the number there like that. Any questions on those different ways to manipulate equations? All right, so let's say we had, for example, let's say we are looking for the equilibrium constant value for this equation here. We're looking for what is the k here. And the only information we are given are this pieces of information here. A plus b goes to 2c plus 2d. The k is 100, and c plus d goes to e plus f, and the k here is 20. All right, so take a minute or two and see what you come up with. We're looking for the k value based off of those other two equations. Take a look, see how we're doing. So essentially what we want to do, right, is basically build this equation from these two equations. So again, we might need to manipulate both of them, one of them, none of them, but we'll see here. In case you're not sure how to do this or approach this, it should be the same way you would approach, again, something like what you did with Hess's law, but depending on, I guess, how you're taught. Let me just tell you, the easiest approach is this. Just basically, you want to make sure everybody's on the correct side, right? And you have the same amount of everybody on the right side. So I would start with E here, and I see E is on the left, and obviously this is the only equation where E is there, and it's on the right-hand side. So right off the bat, I do know I need to reverse it, right, and flip it around. In addition, I don't need one E when I'm done. I need 2. So I also need to multiply by 2 to get me the right amount. So the first thing I'm going to do is reverse this thing, which would be E plus F goes to C plus D. When I reverse it, my equilibrium constant then does what? Becomes 1 over the original value, right? Because I reversed it. So that'll be 1 over 20. In addition, as we just mentioned, I need to also multiply this by 2 to give me the right amount of E. So when I multiply the entire thing here by 2, how does that now affect my equilibrium constant? I need to square it. Again, not multiply by 2, but square it here. So the key here, you want to kind of keep track of everything that you're doing so that you'll hopefully end up with the right stuff. By doing the E, that actually took care of the F, which oftentimes happens. So then I'm going to go to my next one, which would be A. A is on the right-hand side. Once again, here, my A is on the incorrect side. It's on the left, so I need to flip it. I just need 1A, and I have 1A. So all I have to actually do on the second one is reverse it. So that would give me 2C plus 2D. Gives me A plus B. Once again here, all I did to this was reverse it, which means I'm going to take 1 over the original value for the equilibrium constant. I'm out of equations at this point, which means I hopefully should have done it correctly. I hope. Never know. Let's see. All right, we're going to add these two reactions together. Remember, anything on opposite sides of the arrow can cancel. So 2C and 2C will go away. 2D and 2D will go away. That will leave me my 2E plus 2F goes to A plus B. Everybody on the left-hand side of the arrow stays there. Everybody on the right-hand side of the arrow stays there. I'm going to get a couple of numbers here to see what we got going on. So 1 divided by 20, right? And take a little square root action. Going to give me 0.0025. 1 divided by 100. One more zero. Going to give me 0.01, I believe, if I'm not mistaken. And at this point, I can figure out the K for this reaction by, I'll just call this K1 and K2 by taking K1 times K2. So here we're going to multiply, not add. And that would give me 0.0025 times 0.01. Gonna give me a K value of 2.5 times 10. A lot of zeros. 1, 2, 3, 4, 1, 2, 3, 4, 5. Minus 5. In this case. Any questions on manipulating these equations here? The key is really just that, keep it simple, just get everybody to the correct side, get the right amount on both sides. And the other really key is you just got to keep track of what you did and make sure that you adjust the K values accordingly and not screw up like a lot of people do, again, by adding when you should be multiplying and those type of things. Any questions on that one there? Small value, large value K here. Small value, so mainly reactants here, even though it came from 2 reactions that had a pretty large K value, right? But by reversing it and doing all those other things, that direction not going to work so well. Any questions on manipulating equations? Okay. So that is, again, is something that you will have to do. And to be clear, you will have to do that probably in situations where it's not necessarily that type of problem. And I guess what I mean by that is the actual problem itself is not just manipulate the equations, but for regular problems and stuff, you may have to manipulate them to get to the right answer to do the calculation. So as we talked about in terms of writing equilibrium expressions, we usually think about concentration and molarity. And as we talked about earlier as well, again, we want to make sure our pressures are in atmosphere. Remember, there's pretty much just 2 things that end up in the equilibrium expression. That is things that are aqueous, AQ, and things that are gases are the 2 things that you include in the expression. Anything that is a solid or liquid is pretty much just hanging out, not doing much. So it is not included in the equilibrium expression. If I have water in the gas phase, would it be included? It would, because it's in the gas phase. Yeah. So, so sometimes people think water liquid all the time, but they see it maybe in something else and won't include it. Again, if it has a G, it should be included, even if it's water. And you should include it in there. Equilibrium constant, as we talked about, has no units, so it is just a number. But as we did some of the calculations last time, if you end up solving for something else besides the equilibrium constant, like you're solving for a concentration or a pressure, you need to throw the units in there, yeah, for those guys. And they would be the same units as in the problem, what everybody else would be. When we see a value for the equilibrium constant, it is, like I said, specifically for exactly how that reaction is written, whatever are the reactants, whatever are on the product side, it's exactly for those guys being on the proper side. And it is also for a specific temperature. So I think I might have mentioned it, but I'll mention it again. Changing the temperature is the one and kind of only thing that will actually affect the value of the equilibrium constant. And as I might have explained earlier, and we'll maybe talk about it again as well, When we talk about changing the temperature, what we're talking about, the difference in equilibrium constant value is between the two temperatures. So between 25 and 40, for example, you would have two different values for the equilibrium constant. But if you did everything at 40 degrees and kept everything at 40 degrees, the equilibrium constant should always be the same, no matter how much you start with, reactants, products, it doesn't matter. If you kept everybody at 25 degrees Celsius, all the equilibrium constant values that you calculate should be the same. But in comparison between 25 and 40, they would be different numbers for the equilibrium constant value. If a reaction can be expressed as a sum of two or more reactions, like we talked about, again, we're going to be multiplying those K values together. And a couple other things we just talked about, obviously. We take the reciprocal, or 1 over the K value if we reverse the reaction. And once again, the other two things that we talked about there, multiplying by a common number, you're going to take it to the common number, so as the exponent. And if you divide by a common number, you'll take the root of the K value to that common number. K always has the same value at a given temperature, regardless of the amount of reactants and products. And as I mentioned a couple of times, that is kind of hard for people to sort of visualize, because logically speaking, we think, well, I started with a lot more reactants in this run versus on the second run, I didn't use as much. How can I get the same value? So what happens is when it reaches equilibrium, the ratio of those products to reactants will always end up being basically the same. And there's many different ways you could get like the same number, right? You could get the number 2 many different ways. You could take 2 divided by 1 is 2, right? You could get 4 divided by 2 is 2, right? Don't try my math now, but you know, like, I don't know, 18 divided by 9 or something like that, right? But maybe it's 2, something like that. So there's many different ways that you can get the exact same number when you're dealing with sort of a fraction, right? Products over reactants, which is essentially what's happening there. It's just different numbers on top and bottom end up being the same ratio when it's all said and done. So that's why you could have many different sort of starting points in a equilibrium reaction, but it will come to rest, if you will, at equilibrium with the same ratio of products to reactants. The next thing we're going to talk about is our one diversion into a different letter, which is Q. So Q is what is known as the reaction quotient, and Q is basically calculated the exact same way as you calculate the equilibrium constant. So when you calculate Q, which is the reaction quotient, you calculate the exact same way as you would calculate K. And again, you would take your products divided by your reactants. Just like you would calculate K, you would also take the coefficients as the exponents. So everything is identical. It's the identical calculation. It's the identical expression. So you may be wondering, why would we use Q? So we use Q in a couple of situations. The first situation is we're given really initial concentrations of everybody, and we're not really sure if we are at equilibrium or not. So we could calculate Q and compare it to the equilibrium constant, and it will tell us pretty much that thing. It will tell us, are we at equilibrium at this point? And if the answer is no, which it commonly is in these type of problems sometimes, if the answer is no, it will also tell you which way you need to go to reach equilibrium. So Q is used for really those two things. Are we at equilibrium? And which way do we need to go to reach equilibrium? So if you calculate Q and it is greater than K, that tells you that the system is not at equilibrium. And in order to reach equilibrium, you need to make more reactants. If you calculate Q and it actually does equal the equilibrium constant, then it will tell you that you actually are at equilibrium at that point. So even though you may think these are initial concentrations, these are actually the equilibrium concentrations that are going on at this point. If you calculate Q and it's less than the K value, it tells you, once again, you are not at equilibrium. And in order to reach equilibrium, you need to roll down to the products that make more products. So if you line them up like this, if you will, Q and K, and if you remember like reactants, goes to products. It's basically opposite of where this points. Is the way you need to go. So points to the right, you need to go back to the left to make more reactants. This guy points to the left, you need to go back to the right to make products. Or you can flip it around and put K on the left-hand side, then it will point exactly which way you need to go, whichever way you want to do that. So there's really two situations, really, as I mentioned, where we use Q. I call it like a just straight up Q type question, which is pretty much that. Are we at equilibrium? And if not, which way you need to go? We will also see another situation where you should use Q later on when we calculate equilibrium concentrations. It could come up there as well. Because Q is calculated exactly like the equilibrium expression, which means products over reactants, what would I need to calculate Q? I would need the concentrations of everybody, yeah? Because if I don't have the concentrations of everybody or the pressures of everybody, you can do with pressures if you like. If I don't have it, there's no possible way to calculate Q, right? So that's always a thing that you should have in your head. Like if you run across a problem, an equilibrium problem, you got everybody's numbers given to you and they don't tell you it's equilibrium or initial. That's a situation where you could calculate Q. You obviously would also need the K value given to you, right? So that you can compare the two to see if you were there. So those are kind of two important things to be able to sort of use Q. You got to have all the concentrations and you also have to have the K value to compare it to. Any questions on that there? All right, so why don't we try one here? Let's take a few minutes here. So you come up with, we have this reaction on the bottom there, and we're going to be throwing in there 0.249 moles of N2, 3.21 mole times 10 to the minus 2 moles of H2, 6.42 times 10 to the minus 4 moles of NH3. We're going to toss it into a 3.5 liter, give it a nice little shake maybe. They're actually moving around since they're gases anyways. The Kc for this is 1.2. We want to know, is the system at equilibrium? And if it is not, which way does it need to go to reach equilibrium? So once again, Q would be a situation you would want to use here. So see what you come up with. Okay, let's take a look. So in this case, we're given the Kc. We're given, again, not the molarity of everybody, but we do have the moles of everybody and the volume, which means we can get molarity from that. So this is pretty much an optimal straight up Q type problem. So we can start with our expression here. And once again, it is going to be exactly the same way as we would do K. So we'll take our products, which in this case is NH3. Once again, we're going to square it because of the coefficient. We're going to divide it by the concentration of N2 and times it by the concentration of H2, which will also be cubed because of the coefficient. So really, in order to kind of put everything in there, since those brackets mean concentration and molarity, we do need to calculate the molarity of everybody to do that. So we'll start with the concentration of N2. That would be 0.249 moles divided by 3.50 liters. And that's going to get us, we'll call it 0.07114 molar. We'll do the same thing there for our H2. We'll take the moles of our H2, which was 3.21 times 10 to the minus 2 moles, divided by our 3.5 liters. And that will give us we'll go with 0.009171, take it to a few digits. And lastly, we'll do our concentration here of our NH3, which would be 6.42 times 10 to the minus 4 moles divided by 3.50 liters there. That's going to get us 0.0001834 molar here. First off, any questions on that part of the calculation there? All right, now that we have all the concentrations, we can now use our Q expression there to calculate our Q. So let's do that. Flip a page here. All right, so once again, our Q is the concentration of NH3 squared divided by the concentration of N2 times H2 cubed. Put in our numbers from the previous page there, that would give us 0.07114 up on top, which we will square. We'll divide it by our N2. I think I put the wrong one there, huh? Yes, I did. And it should be NH3. Sorry about that. Get the NH3 up there on top. So that one should be 0.000, I think, 1834. There we go. Now divided by N2, so this guy should go on the bottom, 0.7114. And our H2, which would be 0.009171, and we want to cube that guy. All right, I think I got my numbers in the right spot there. All right, so taking the top by there, 0.0001834. We're going to do a little square action on it. We're going to divide it by 0.07114. We're going to divide it by 0.009171, and we're going to cube that guy there. And that is going to give us a Q value of 0.613, we'll call it. Any questions on that there? At this point, we want to compare it to the K value that was given to us, which was 1.2. So the KC given to us was 1.2. In this case, my Q is greater than, less than, equal to. It is less than my K. That tells me, first off, I am not at equilibrium. And which way do I need to go to reach equilibrium here? I need to go opposite of where that's pointing. So I need to go towards the product side there to reach equilibrium now. Any questions on that calculation there? So like I said, pretty much two situations for Q, a question just like this, which usually asks those two things, you know, are you at equilibrium, which way to go? And again, it will pop up later here in the next type of calculation we're talking about. So whenever you have everything given to you, probably at some point, you should probably calculate Q, make sure you understand what is going on in terms of the reaction. Any questions on Q, the reaction quotient? Then it is time to talk about the calculation of the year here. All right, so we're now going to talk about solving equilibrium problems and trying to solve for either equilibrium concentrations or equilibrium pressures. Once again, you will be given situations where you're just given sort of the initial or starting amounts of everybody. You need to basically figure out what the equilibrium concentrations are. So when we do this, we usually try to do it in a situation where we have pretty much just one sort of unknown factor. And that unknown factor is X. And the way that we solve these equilibrium problems is we use what is referred to as an ICE table, is usually what we use. And an ICE table stands for initial, change, and equilibrium, basically. And we use these ICE tables to help us calculate the equilibrium concentrations, our pressures from starting amounts. And it is that change part that we represent with an X. So a lot of times when we do these ICE tables, the goal of the ICE tables is to figure out what X is, which is really the change. And then that will allow you to calculate pretty much the equilibrium concentrations. This is going to require math, yes. And it may require several different ways to solve these type of tables to solve for X. The good news is probably the most complicated part that we will do is the quadratic formula. Yes, so we all maybe remember that ish. That we got like a X is equal to minus B plus or minus the square root of B squared minus 4AC divided by 2A. And that is off of a AX squared plus BX plus C type of situation of an equation where A, B, and C are those values that we get. Yeah. By the way, when we use the quadratic equation or formula here, how many answers do we get? You do get 2 answers. One answer will make sense. One will not make sense in these situations. So I would say mathematically, that is maybe the most complicated move that we will do as we solve these ICE tables, which is not too bad. You don't always have to use a quadratic formula. There are other ways to solve them, but you can always use it if you like, if you're a fan of it. But there will definitely be times where you do need to use it. So let's talk a little bit about sort of a reaction like A plus B goes to 2C. And let's just say the K here was 100, right? So let's say that we initially were told that we started with an initial concentration of A that's 0.1 molar and B that is also, we'll start with 0.1 molar, right? So the way that we would do this ICE table is we would take our equation there and we would set up our ICE table as follows. Initially, we would put in our concentration. So this would be 0.1. This would be 0.1. Now there was no mention of C, right? So in this case, if you're only given reactants, it is probably safe to assume you have how much of C? 0. Yeah, so it's probably safe to assume you don't have anything going on yet. It's pretty much all reactants at this point. Because of that sort of assumption, which is probably correct in most cases, we would expect which part of this reaction to occur. And what I mean by that, would we expect the forward direction to occur or the reverse direction to occur? So if all you have is reactants, what should you start making? Products, which means the reaction should go in the forward direction at this point. It cannot go in the reverse direction because you don't have any products yet, right? So the only way it could go backwards is you got to make some products to begin with. That means as time goes on here, the amount of A and B, should it get less or more? Should be less. I think I heard somebody whisper, say less would be the right answer there. The amount of products should start to increase, as we talked about. The way we represent sort of decreasing and increasing in the ICE table is by minuses and pluses. So on the reactant side, everybody should be minuses. On the product side, everybody should be pluses as they are adding. And that occurs in the change part of the table. And in the change part of the table, that is where we typically use the letter X to represent the change. So this is going to be minus X, and this will be plus 2X. I put the 2 there because the coefficient right here is a 2. Coefficient here is a 1. And a coefficient here is a 1, right? Although you don't usually write it. In your wonderful experience with chemistry, where did we use the coefficients to do calculations? Is what type of relationship the coefficients? It is the mole to mole relationship. It's the stoichiometry. And it's really important when you do an ICE table in the change part, you've got to make sure that you include the coefficients Otherwise, you have, frankly, the wrong mole-to-mole relationship and the wrong stoichiometry. Yeah. So that is why we include the coefficients to take care of the stoichiometry. Also, why maybe some of you learn ice tables when you're doing limiting reagents. Anyone? No? Just me. I teach it. I know when I teach that class, I teach it. Because I know you're just going to end up here doing it again. So why not just teach it then? But you can use this for like stoichiometry and limiting reagents, ice tables. So we use the minuses on the left-hand side because those guys should be decreasing. We use the pluses on the right-hand side, so they should be increasing. We want to make sure we take the coefficients there to make sure we got the right mole-to-mole relationship. And now we can get to the equilibrium part, which is simply just bringing everybody down. So this would give me 0.1 minus x, 0.1 minus x, and 2x. Any questions on the ice table there? I got a bunch of x's. I kind of need to figure out what x is. So the way that I do this is we're going to use the equilibrium expression to help us do that. So if we were to write the equilibrium expression here in my made-up problem, it would be K is equal to the concentration of C that is squared, right? Divided by A divided by B, and this would equal my made-up number there of 100. At this point, what you would do is you would take everybody here on the equilibrium line and you would put it into this expression. You can put everybody into their proper places in the expression, which means in this case, I would have 2x that would be squared divided by A, which is 0.1 minus x, 0.1 minus x, and that would equal 100 at this point. At this point, it's now a math problem. We need to solve for x, basically. So we'll save doing this one because I made up numbers. I think it would work out, but we'll save it. But basically, you can go through math here and solve for x. We have plenty of examples where we'll do the math in just a second. By the way, just looking at that, what would be the best way to solve that? Anyone? Yeah, I would take a big square root of both sides rather than a quadratic move. Yeah, because it is a perfect square on both sides. That would be a good move. And obviously at that point, you could solve for x. So we'll do some examples here in just a second where we'll go through all the numbers. But once you do solve for x, x does represent a change. And why x is important here is the x value that you get once you solve for it is every single x value that we see here in our table at our equilibrium line. So now that we know what x is, we could simply go back and subtract 0.1 from x for the A, we could subtract 0.1 from x for the B's concentration at equilibrium, and we could take 2 times x for the concentration of C here, and that would allow us now to have obviously the equilibrium concentrations of everybody. Any questions on the general outline of how an ice table works here? So the key is the math part. Troublesome sometimes for people. This is one way we could solve it. Perfect square. Quadratic formula is another way. The only way, and we'll talk about another way as well as we go through it. The only way that we will not solve ice tables in this class is through a process known as successive approximation, which means if you're really crappy at that, you will be there all day trying to figure it out. So successive approximation basically means, you throw a number in and then solve for x, and you keep throwing numbers in until the number you throw in and the number you get out when you solve for x is the same number, which can maybe many roads down the way there. So these are some common ways, and we'll talk about another way along the way. So why don't we try a real one here with some numbers? There we go. Let's go with this one here. So why don't you take a few minutes here and see what you come up with. We got the reaction here, Br2 to 2Br. We have the K value is 7, and the initial concentration of Br2 is 0.663. We want to calculate the equilibrium concentrations of everybody here. So since we sort of demoed one just a second ago, follow that process. Let's see what you come up with. let's kind of see how you're doing. So once again here, we're looking for equilibrium concentrations. So that usually does mean an ice table is what you need to do. We could write our equilibrium expression here by taking obviously our products, which in this case would be BR. We would square it because of the coefficient divided by the concentration of BR2. And in this particular case, this is going to equal 7. At this point, they gave us the concentration, so we don't have to do any conversion there. So we'll start with our ice table, which will look something like this: BR2 to BR. Initially here, we have 0.663. Once again, we were not given anything in terms of BR, so it is pretty much safe to assume that this is going to be 0 to begin with. That also means it should be safe to assume that the reaction is heading to the product side, right, in the forward direction, which means our reactants would be negatives and our products would be positive. If we were given the concentration of the BR in this case, what should we actually calculate first? We probably should calculate Q that we just did, right? So this is the other situation where Q could come into play. A problem like this, where you're given the concentrations of everybody, you should calculate Q. Why would I want to calculate Q? Well, the answer probably is going to tell you you're not at equilibrium. Otherwise, it wouldn't be much of a problem. But the other important information that you could get from that is which way it needs to go to reach equilibrium, right? So if you happen to calculate Q, which you could not do in this case, but if you were given the information to do so, and it said you need to go to reactants, what is that going to change? It's going to change the change part of it, right? Because if it's going to reactants, my products are going to get smaller, right? And my reactants are going to get bigger, which means minuses will be on the product side, positives will be on the reactant side. So that is the second place where kind of Q could come into play, that you really should calculate it. The good news is probably 90 some odd % of the time, it's probably almost a safe bet to know that it's going towards the product side, but you potentially could be going the other way. So keep that in mind as you go through these sort of equilibrium problems. If you are given the starting amounts of everybody, you should take a moment to calculate Q, so that when you get to the change part of the table, you can feel confident that it is heading, in that direction and needs to go in that direction. Any questions on that there? So once again, here, we don't have that situation. We have nothing given to us in terms of products. So it is safe to assume that the reaction is heading in the product side way. That means we should have less reactants. So we're going to represent that by minus X. And on our product side, plus 2X, once again, using the coefficient there to make sure we have the right mole to mole relationship. That means that we are ready to bring everybody down here. That's going to be 0.663 minus X and a 2X. Any questions on the ice table there? At this point, the goal here is to really solve for X. So we're going to put it into our expression. So I'm just going to flip the page here to do that. So once again, our expression was BR squared divided by BR2, and that equals 7. So put it in our numbers there for, excuse me, our equilibrium line for BR. That would give us 2X that's going to be squared, divided by 0.663 minus X, and that is going to equal 7 in this case. Is this a perfect square? It is not, right? So in this case, we do need to multiply the bottom to the other side, yeah? So that is basically what we want to do. We're going to take 4X squared up on top, going to multiply everything from the bottom to the other side. When we do that, I believe it's 4.641 minus 7X, yeah? At this point, to solve it mathematically, we are heading towards the quadratic formula here. That means we need to get everybody to the same side of the equal sign, right? I'm going to bring everybody back this way. That keeps this guy positive. You don't have to do that, but most people like to keep it positive. So that would give me 4X squared plus 7X minus 4.641 equals 0. And again, that's basically taking both of those guys from the right-hand side, adding and subtracting them back over to the other side as we did it. This is the form of a quadratic formula of ax squared plus bx plus c, right? Equals 0. That means that in terms of my a, b, and c here, my a is 4, my b is 7, and important here, my c is the negative. Yes, so you got to keep the negative with that number. So it is the negative version of it. That is going to go into our quadratic formula there. And that's going to be x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a would be good. All right, so popping in our numbers there that were highlighted for a, b, and c, we get x is equal to minus 7 plus or minus, if you do everything inside the square root, you end up with something like 123.256, which then when you take the square root of it, yields you something like 11.10, I believe. Yeah. So inside, outside the square root there. All divided by 2 times 4, which would be 8. Any questions on that there? As we talked about before, we get 2 answers, one going the plus root and one going the minus root. Taking us on our plus journey there, it's going to be negative 7 plus 11.10 divided by 8. Going to give us an x value of 0.51. We'll call it 3. Or if we go the subtraction route there, that's going to give us negative 7 minus 11.1 divided by 8. Going to give us a negative 2.26, we'll call it. First off, any questions on the solving part of that there? Now, at this point, you will get 2 numbers. In this case, one number is positive, one number is negative. Your other options are all the options. So you could get 2 positive numbers, get 2 negative numbers. One of them should not make sense. And which one should not make sense here? If you're not sure, let us pop up here the ice table one more time here. And we're just going to put up the equilibrium line of the ice table, which is 0.663 minus x and basically 2x. Technically speaking, I would go and put both of those values into x. Which one would be not a great one to be used? What happens when I take this one and I put it into here? I get a negative 4 and some change. Can you have a negative concentration? You cannot, which means this one would probably be not the best choice there, right? So you cannot have a negative concentration. That means the winner here is going to be the 0.513, and that's going to be our x value at this point. So we're now going to use that, and we're going to put it into our equilibrium line for each of them and solve for our equilibrium concentrations. And if we do that for BR2, it was 0.663 minus x, which is 0.663 minus 0.513 molar, going to get us 0.150 molar. For our BR, it was 2 times x, which gives us 2 times 0.513 molar. And that gives us 2 times 0.513. We'll call it 1.03 molar. These would represent then the equilibrium concentrations of everybody there. Any questions on that one there? Now, it is math, right? So math's good for a couple things. One thing math is good at is you oftentimes can check to see if perhaps your answer makes sense. if I wanted to check to see if my answer made sense, what could I do? Yeah, so now that we have these guys, which are the equilibrium concentrations, I could go back to my K expression, which was my BR squared divided by my BR2, and it should equal 7 when I put those numbers in. So if I put it in, I end up with 1.03 squared, I think, right? Divided by 0.150. And I got pretty much 7 as well. Yeah. Will be perfect. It won't be with rounding, but it should definitely be ballpark perfect. Yeah. Like you didn't show up at the wrong ballpark. Yes. This looks like a great game, but I don't have tickets to this game. I'm like, should be way over there. So, you know, if you do have time, it's a good idea to kind of throw it back into the equilibrium expression. There is a lot of places where things could go bad in the calculation part. This, I would say, was a fairly simple quadratic equation here and formula to solve for. There's ones where there is a ton of factoring and stuff that you got to do before you get there. So it's always a good idea to kind of check it when it's all said and done. Any questions on that there? Okay, so now we're getting to the end. We'll lay it up. I think there